This video will focus on the learning target. I can determine the bond polarity of the individual bonds within molecules. So when it comes to types of bonds, we have ionic bond and we have covalent bonds. But for covalent bonds, as I've mentioned, they could share equally or unequally, depending on the scenario. Now, so far we've seen things like for ionic compounds, these tend to happen with metals and nonmetals. Covalent compounds tend to happen with only nonmetals. But there are other tools in our toolkit that we can use to determine what type of bond that two elements will engage in when they come together. Okay. Essentially, if you remember the three scenarios, we either have a scenario where two elements come together and they share the electrons equally because they both have a pretty equal pull on them. They could also share unequally, meaning one element tends to pull the electrons toward themselves more frequently than the other one, or you could have a full transfer, so one completely removes the electron from the other. In all of these cases, I'm really referring to electronegativity, that ability to pull. Either I'm pulling equally, unequally, or so unequally I actually transfer. So the type of bond can actually be not just assumed or presumed based on the type of elements that are joining in a bond together, but it can actually be calculated using a difference in electronegativity. Okay? So the calculation for this, we usually call it the DEN. So DEN stands for difference in electronegativity, okay? And DEN is always the absolute value of your two electronegativities subtracted. So always take the bigger from the smaller to figure out what the difference is. So if I were bonding like fluorine, say for example, with hydrogen, okay, if those were my two things that were bonding, it would be 4 minus 2.2. Okay. So that's a potential type of calculation. Now, depending on what number you get, we can determine the type of bond based on this scale. Okay? So nonpolar covalent things are where I'm sharing equally, right? Neither one is winning, which means the difference between them is less than 0.4. Okay, so essentially you're all the way up to 0.399 repeating, right? If I'm less than 0.4, I am on this side in the nonpolar covalent side. Then if I'm between 0.4 and about 2.0, I would be polar. So what that means is there's enough difference in electronegativity that the electrons tend to reside on one side over the other. And then if I'm so I would say this is, so it's less, yeah, so it's up to like 1.99 again, okay? And then if I'm at 2.0 or over, so once I get to 2, I'm ionic. Now, truthfully, in this region, it's a question of the size of the atom and in relation to the pull to really what type of bond is created. Do I have a full separation or just a partial separation? So do you know this isn't like a hard and fast boop from 1.9 to 2. Oftentimes I say from 0.4 to about 1.7 is for sure polar covalent. And then from 1.7 to 2.0, you kind of have to look at what's being bonded, assuming that ionic is always going to be that non-metal, right, with a metal. So sometimes a non-metal with a metal isn't going all the way up to 2.0, but they'll still make ionic. Okay? In our class, we will use the 0.4 and the 2.0 just in general, so don't worry too much. Why is this important? Well, polar bonds result in an area of negativity where electrons are being pulled, an area of positivity where the electrons are being pulled away from. Okay? And in chemistry, essentially everything we've seen is dictated by this attraction between positive and negative. So if I'm creating even partial positives and negatives, there's going to be a consequence. Okay? So as we have, let's say for that hydrogen fluoride example, that one ends up being polar. Fluorine is more electronegative, so it ends up pulling the electrons towards it. So I have a larger area where electrons tend to reside over here and like a smaller area where the electrons are residing over there. As a result, we have partial charges, not full point charges, but just partial ones. And the way partial charges are written are this weird lowercase delta. So partial negative is a lowercase delta in Greek, and then partial positive. So over here, the fluorine, this one would be partially negative because the electrons are being pulled in that direction, and the hydrogen would be a partial positive. So the other thing we can do based on these areas of positivity and areas of negativity is talk about the fact that we're creating something called poles. So we think about poles, oftentimes people think about the North Pole and South Pole or the opposite poles on a magnet, and it's the same thing in this case, right? As I have that hydrogen fluoride example, I'm pulling my electrons on one side, creating a negative over here, leaving behind a side that doesn't have as many electrons, so leaving behind a positive. And this creates a dipolar situation. I have two poles. We also call that a dipole moment, a moment when I have two poles, okay? And something that's created in chemistry is a dipole moment arrow, which is an arrow that points to the direction of pull. So I'm pointing toward the fluorine because that's where I'm pulling. And then the back of your arrow ends up being this little plus sign, indicating the fact that I'm pulling toward the negative and the back is positive. Okay, so that's how you create a dipole moment arrow. You figure out where the negative is, where the positive is, and then have the arrow point to the negative. We can do this even on a more complicated structure that has multiple bonds. In this case, the oxygen is more negative than either hydrogen. Now I'm pulling along the bonds towards the oxygen. So these are the dipole moment arrows for water. So here are a couple examples of those two elements bonded. And the question is, are they polar, nonpolar, or ionic? And if they are polar, we should make some dipole moment arrows. So to determine the type of bond, we're going to look at their electronegativities. So bromine has an electronegativity of 2.96. Oh my gosh. And then the sulfur has an electronegativity of 2.58. So if we calculate our den, which is our difference in electronegativity, which is to take the bigger one and subtract the smaller one from it, we end up with a difference of only 0.38. 0.38 means this is a non-polar bond, which means no dipoles, no arrow needed. Now the oxygen-nitrogen bond literally ends up with an exact of 0.4, which means that's just enough to become polar. And if I look at their two electronegativities, oxygen is the bigger electronegativity, so it ends up being the negative one, and nitrogen is the smaller electronegativity, so it's the positive one. So my dipole moment arrow would be pointing toward the oxygen because that's the negative side. Bromine and bromine are exactly identical, so that's going to end up being nonpolar. I don't even have to worry about it. And then the difference between chlorine and silicon is 1.26, which puts me in my polar region. Okay, if I look at the table, I see that chlorine is the negative one and silicon is the positive one. So my arrow is going to point towards the chlorine again, away from the silicon. There's your examples of how to figure out bond polarity. Go ahead and do the quiz and have a nice night.